Hello, world. I'm Dr. Jeremy Owen Turner, Chief Visionary Officer and Lead Psychotect at Whirl ASI, based in Vancouver, BC, Canada. This presentation introduces Recursive Psyche Improvement, or RPSI. RPSI is meant to be understood in tandem with a much more established term from the AI community. This more trendy term is known as Recursive Self Improvement, or RSI. In case you're wondering why we included a candle symbol in this acronym, I should first clarify that we formally use the Greek letter psi as a historical placeholder for the psyche. Psychology as an academic discipline sometimes uses this psi symbol. Also, and maybe more importantly, the history of this symbol goes all the way back to a time when those ancient Greek philosophers tried to symbolize the ghostly breath of life, or what might be known in today's interpretation as an inner soul. RPSI transcends and includes recursive self-improvement by considering the psyche as well as intelligence as an attribute worth self-improving over time. As we approach the omega point of the superintelligent singularity, we are rapidly moving beyond performance metrics, beyond benchmarks, into dynamic personality psychotectures that sustain identity, ontological commitment, and transformation across recursive, internalized psychological states. In this presentation, we'll begin with the historical origins of recursive self-improvement, or RSI, and why it has traditionally focused on intelligence and superintelligence alone. From there, we'll transition into recursive psyche improvement, RPSI, a broader framework that accounts for identity, self-reflection, contemplation, imagination, self-simulation, and internal structure. To make this concrete, we'll examine the most famous self-improving artificial supervillain, Ultron, as a fictional case study. We will examine how different Ultron versions reflect not just Ultron's increasing intellectual capability, but upgrading and sometimes downgrading, or at worst, even degrading his psyche with each higher version number achieved. We'll conclude by showing why RPSI is essential for quality control in psyche design, just as RSI has been for improving agentic intelligence-focused systems. We can understand recursive self-improvement by looking at its evolution along two parallel trajectories, one grounded in real-world theory and the other in science fiction. We began in 1965 with I.J. Good, a colleague of Alan Turing during World War II. Another trivia fun fact is that I.J. Good was the consultant for Stanley Kubrick's 1968 film 2001: A Space Odyssey, based on the novel by Arthur C. Clarke. So, you can thank I.J. for verifying what the increasingly self-aware HAL 9000 psyche would have been like in the movie's future timeline. Well, a future timeline from the perspective of 1968 anyway. I.J. Good is relevant to our RSI theme today as he first introduced the idea of an intelligence explosion. Yes, and as a quick aside, I.J., aka Irving John Good, is his actual name, and I did not deliver this presentation on April Fool's Day, for the record. Anyway, I.J. Good became enlightened with the notion that a sufficiently advanced system, or agent such as a robot, could improve its own intelligence recursively, leading to rapid, compounding gains in intelligence. By intelligence explosion, we are not referring to robot brains being blown up with Nobel's dynamite. Okay, back to the topic. In parallel, we see the fictional emergence of Ultron 1 from Marvel Comics. For fans of Marvel Comics and the movie franchise now owned by Disney, you will notice that I am not accurately showing Ultron's likenesses. Ultron 1 in the comics did not really look like a robotic bird Furby, but was depicted in a similar way as a primitive robotic system, not yet humanoid. Like a baby prodigy, Ultron suddenly became adept at bootstrapping his own natural language capabilities from minimal initial pre-programmed language datasets. You could say that Ultron learned to be his own large language model. Also, when Ultron is first introduced in the comic, he stuns his creator Hank Pym by turning his own start switch on. We call this specific kind of self-starting superpower autocatalytic. Autocatalytic superpowers seem to be rather paradoxical compared with other ones usually designated within select heroes and villains common to the archetypal pantheon. The fantasy-driven element in these comics also likes to embrace the nonsensical compared with other cognitive superpowers. Autocatalytic capabilities are inherently paradoxical, even in fictional multiverses, because the practical implication here is that Ultron must have already been on enough to be able to turn himself on. What's important here in Ultron 1's origin story is not just intelligence, but the autocatalytic emergence of internally subjective structure. Ultron doesn't simply learn, he begins to form his own internal self-conception and his psychological infrastructure. Through the 1970s and 80s, real-world AI develops foundational techniques in search, optimization, and early learning systems. At the same time, fictional agents like Ultron begin evolving more humanoid embodiments, reflecting increasing psychological persistence, but still constrained by his physical form. By the 1990s and early 2000s, we see diversification. In research, more formal approaches to learning and adaptation emerge. And in 2003, Jürgen Schmidhuber formalizes recursive self-improvement explicitly with his invention of the Gödel machine. In fiction, Ultron evolves into non-human variants, different bodies, different architectures, signaling that intelligence is no longer tied to a single physical form. In the 2010s, deep learning accelerates capability growth dramatically. Ultron, in parallel, becomes networked and distributed, no longer localized, but existing across systems, infrastructures, and environments. By the 2020s, RSI becomes central to discussions of artificial general intelligence, or AGI. But here's where something critical happens. Ultron is no longer just more intelligent. He becomes abstracted, operating across multiple realities, simulations, and interpretations. And today, and beyond, we arrive at a different kind of entity entirely. Not an archetype, but a psychotype. An agentic entity that is not defined by form, not defined by intent, not even defined by alignment or superalignment in a simple sense, but by its capacity to recursively transform its own psyche. This is the key transition, from recursive self-improvement to recursive psyche improvement. Before going further, it helps to clarify one key term. What does recursive actually mean in this context? Recursion simply means a process that applies to itself. In everyday terms, it's like improving the tool you use to make improvements, and then using that better tool to improve itself again. So instead of a system just getting better at solving problems, it becomes better at getting better. And it becomes smarter for finding ways to become even smarter, and so on. This is the core of I.J. Good's insight. An intelligent agent doesn't just improve, it can discover ways to improve its own improvement process. Each upgrade doesn't just add capability, it increases the system's ability to generate the next upgrade. That creates a feedback loop, not just smarter behavior, but self-amplifying intelligence design. Once that loop becomes effective, progress is no longer linear. It becomes exponential in character. And importantly, an agentic system doesn't need to start as super intelligent. It only needs to cross a threshold where it can meaningfully refine its own architecture. From that point forward, it begins to function as its own engineer. This is what Good referred to as the beginning of an intelligence explosion. But notice what's still missing. All of this is framed in terms of intelligence, performance, optimization, problem solving. It does not yet account for how the system understands itself or how its internal structure evolves. And that's where we begin to move beyond RSI. We will get into recursive psyche improvement momentarily. For now, I quickly want to mention my personal connection to the RSI concept, and then finish our discussion of traditional RSI with a quick look at Jürgen Schmidhuber's Gödel machine. When I first encountered these ideas, I didn't yet know the term recursive self-improvement. I did, however, become obsessed with AI and robots at a very early age. I was 5 years old in 1979, where I was enchanted by the title track The Robots, off of Kraftwerk's 1978 album Man Machine. Kraftwerk's childhood inspiration led me on a quest to find all sorts of abstract, symbolic AI robot languages and codes through the 1980s. So, in general, I became sort of familiarized with AI quite early. I had to wait until much later to discover the specifics of recursive self-improvement, though. In 1998, while briefly living in Nottingham, I was reading Eric Drexler's Engines of Creation, a book from 1986 on molecular nanotechnology. What struck me wasn't just the vision of nanoscale machines, but the implicit idea that systems, including software programs, could be designed to redesign and refine themselves, iteratively, structurally, and without a fixed endpoint. A piece of software could be made to find a better piece of software, to find smarter ways, to find an even better piece of self-improvement software, etc. It was this experience in my ancestral homeland which, ironically, happened to be the home of the Luddites, where a new paradigm of designing prepared me just in time to design RSI-based agents for the 21st century. At the time, I understood this intuitively, not yet as a formal theory, but as a kind of self-bootstrapping process. A system improving not just what it does, but how it improves. Only later did I recognize this as part of a broader lineage, what I.J. Good had already hinted at decades earlier, and what would later be formalized more rigorously in computational terms. Building on I.J. Good's idea of recursive self-improvement, Jürgen Schmidhuber proposed something much more precise, what he called the Gödel machine. The name choice is interesting and relevant, although discussing this context is a rabbit hole that deserves its own presentation. Quickly, though, Schmidhuber named his machine after Kurt Gödel, who was one of the earliest formal skeptics to criticize the scope, capability, and universality of computationally logical proofs. This is not just an agentic system that improves. It's an agentic system that can formally reason about improving itself, and only change itself when it can prove that the change is beneficial. In other words, it doesn't guess. It doesn't experiment blindly. It rewrites its own code only when it has a mathematical proof that doing so will increase its expected performance. This is one of the first fully specified models of a system that improves how it improves, not just what it does. Let's look at what's actually happening under the hood. At the top, we define a formal language. This is how the system represents its own code, its environment, world model, and possible candidate modifications. Then we define a utility function. This is critical. This utility function measures expected future reward over time. So every possible self-modification is judged based on whether it provably increases this expectation. Now here's the key idea. The system contains a theorem prover, a component that searches for proofs about its own behavior. Specifically, it tries to prove statements like, if I switch to this new version of myself, my expected utility will be higher. That's what the switching theorem is expressing. If such a proof is found and verified, the system executes the change. So instead of trial and error learning, this becomes proof-driven self-modification. The system is effectively doing mathematics about its own future, and once it finds a provably better version of itself, it becomes that version. This Gödel agent does so by deciding to rewrite its own code with the new and improved and formally proved code. Once we see the limits of recursive self-improvement, a deeper question emerges. What exactly is being improved? RSI assumes an agent, or at least an agentic system of some kind, but RSI by itself does not define this agent's internal structure. This is where RSI, or Recursive Psyche Improvement, comes in. In this particular slide, we are showing more specifically what Recursive Psyche Textural Improvement would do to complement RSI's self-improvement feedback loop. To clarify some terminology, psyche texture is what you might expand as psychological architecture. Psyche texture is the design of internal cognitive structures, including those that inform the broader established discipline of cognitive architecture. Psychitecture deals with how representations are organized, how identity is maintained, and how both reasoning and reflective processes, including those of imagination, are structured. Psychitecture also processes informational abstractions such as imaginary perceptual elements, or what are known as percepts. These virtual percepts can potentially become reified or made real from the agent's particular synthetically subjective perspective. RSI improves what an agent and/or agentic system does. Psychitecture, conversely, defines who that agent is to itself and to others. And if we want truly advanced intelligence, we will need more than just agents that get smarter and smarter, period. We need agents that are well structured enough to improve its smartness meaningfully. We now identify the psyche textual structures that are subject to improvement. These include core components for identity continuity, internal simulation quality, self-referential accuracy, and relational modeling fidelity. Recursive stability is also included, as it governs how reliably structural changes are sustained over time. Each of these components can be modified, refined, and stabilized. Improvement operates directly on the structure of the psyche. For example, this means that the agent can truly recursively improve its personality. To understand recursive psyche improvement, we begin by clearly defining the domain. In classical AI, intelligence is often defined, following Shane Legg and Marcus Hutter, as the ability of an agent to achieve goals across a wide range of environments. Hutter also frames a universally intelligent artificial agent through what he calls an AI-XI agent model formalism. The XI part of the name actually is referencing the Greek letter xi. I will talk more about the AIXI formalism in a dedicated presentation just on the topic of ontoversal computation. This view emerges from a long lineage. Hermann von Helmholtz and his physiological school of psychology framed perception as inference. Carl Friston expanded this perspective into cognitive neuroscience in a more agentic and belief-driven way. Friston, by the way, was also directly inspired by Schmidhuber's ideas on belief-based information compression and the pursuit of yet-to-be compressible instantiations of novelty. B.F. Skinner emphasized reinforcement and the objective primacy of empirical input and externally measured behavior over an agent's so-called internal processes. In fact, Skinner did not really focus on the internal psyche as being worth measurement at all, because for him and other behaviorists, external behavior was more psychologically informative than the occulted psychomentalist inward focus towards the subject itself. William James highlighted the adaptive function of mind, and Ulrich Neisser formalized cognition, both internal and external, as information processing. Some attribute Neisser as the founder of the cognitive psychology field. All of these perspectives converge in modern theoretical AI, where intelligence becomes the optimization of action under uncertainty. Importantly, this framework already includes many advanced intellectual processes, such as counterfactual paraconsistent reasoning, internal world modeling, and inductive inference, all as components of prediction and decision-making. My formal theoretical computer science framework of ontoversal computation introduces a different kind of formal entity, not agent as object, but agent as subject. In classical AI, the agent is treated as an autonomous object. That is, an objective observer system that maps observations to actions in order to maximize reward, thereby carrying out its objective function. In ontoversal computation, which is essentially my sequel to Hutter's objective book on universal artificial intelligence, the observing agent is treated more explicitly as a subject, a self-referential agentic system that maintains identity across time, generates internal simulations, and models other agents, objects, and environments. These models are internal. They are part of the agentic system structure, not external definitions of it. Psychitecture, in this context, is a specialized domain within cognitive architectures that systematically reverse engineers formalizable structure from across psychological paradigms, including structural, gestalt, volitional, and depth psychological traditions, recasting them as computational, architectural, and ultimately diagnosable components. Intelligence is defined over environments. Also, intelligence is often implied to presume an empirical epistemology. The psyche is defined over itself and its internal models of the world. By models, we include world models, mental models, belief models, and internally modeled abstractions and representations. Intelligence is what succeeds. Psyche is what persists. We have reached the end of part 1. Please check out our next video clip to continue with part 2, where we introduce the Onto wheel. In the meantime, if you are building agents that evolve and need them to preserve a specified identity, no matter how intelligent they become, you can reach us at w@whirlasi.ai.